Everybody has a Tuesday visit, but they all get done at 1 in case it starts at 1.
All right, so here we are on the 9th of July. Hope you all had a good weekend. I had a great weekend, more or less. We made it through, and of course, 4th of July, exciting. Could be. Fireworks, we had some good fireworks. So, yeah. What's going to happen now is kind of an adjustment, okay? Because I had mentioned to you that we were going to move homework set 11 to be due on Wednesday instead of due today. And that is the situation. But after some consideration, I'm going to move homework set number 12 to be on Monday. So then we won't have 11 and 12 due on Wednesday. We'll just have 11 due on Wednesday. And then we're just going to take homework set number 13 out. So we're not going to do that homework set. Hopefully we'll still talk about it and think about it some. Because it does kind of influence some of the later stuff that we're going to be doing. But it's not as important as homework sets 11 and 12. So, yeah, we'll get that squared away. And it's certainly possible that it's now going to make life easier, but maybe not quite as difficult is okay right now. So that's what we're going to do. So what we're going to do is talk about homework set number 11, go through that in a pretty good amount of detail now, and try to make sure that you understand everything. And then we'll do a bunch of problems like the ones in homework set 11. So then you'll have all the stuff to make that really, really good for this, because it is, after all, a new topic. And it's been a week since you've been in here. So let's see if we can make that happen. But in order to make that happen, I need to go get something off the printer. I forgot. So give me a minute. I'm going to go get my stuff off the printer, and I'll be back. Yeah, I'll leave the video running.
Just in case what?
I don't know, I didn't see it.
I did it and then I was here so bad.
Oh, okay.
Because I wasn't going to convert this barrel. Yeah. So I wasn't going to drive back and forth. Yeah. It's kind of showing off. Yeah, so what makes you
I like took off, and I was like, all right, well, I gotta do something.
And I've never gone late.
Yeah.
I wanted like a color.
Where'd you go?
Orange Pearl.
So you
It's like
I've always wanted to go to a Rose, but I never did because my mom was a cosmetologist.
Oh, yeah.
So she would be really fun if I went.
I love.
She's trying
Yeah, oh my God, okay, so, there's another one out to Riverside, so I'm saying, I might have talked to you. And then I just had thought, before that, my sister had wanted to take kids for Riverfest.
Right.
When we got there, it was really hot, and the boys were really crabby, so we just went far enough to find our park, and then we left. But then we were like, well, this is enough space. So there was still a space behind us, so we were like, oh, well, let's just run to the north. And as we were pulling back into the forest, from the forest, it just down.
All right, so now we're all set. We thought we were set before, but we're not. Now we are.
And then my mom's power was out for like 2 hours.
I did, but I couldn't give it out. Yeah, like, you know, so bad. Like, they give it to you. Like, I just they're not the same as
That's possible. I think.
Can I grab this paper?
Yes.
I just took a couple hours.
Danielle? While you're up here. Abby.
Thank you.
Well, sure, why not?
That's so, that's even like,
All right, so we're going to do this problem right here. And we're going to use the sheet of paper that I handed out to you in order to go through this problem. So when we're talking about doing hypothesis testing, once again, the idea here is that we have a traditional way of figuring out how to make decisions. If we use confidence intervals give us something that we can use. I want to know what that is. What's the purpose of confidence intervals?
understand disease word.
No. The purpose of the confidence interval. What's the purpose of the confidence interval? I'm going to ask you that every day from now until the end of the term. I'm going to put it on test number 3. I'm going to put it on test number 4. I'm going to ask you every day from now until the end of the term, most likely, what is the purpose of the confidence interval? To measure something about a population. Okay? So we're using a sample to understand something about a population. What are the 3 things that we can measure right now in a confidence interval? Proportion, mean, and standard deviation. What does proportion tell us? What kinds of data are we talking about when we're talking about doing proportions? There's another question. Okay, when we're talking about a proportion, what is it that we are measuring? No, all of these things could be populations. I want to know what happens when I measure a proportion. What kind of data are we talking about? An observed probability versus the population proportion. Well, that's true, but we want to be a little bit more specific about this. When I'm measuring a proportion, I'm measuring a percent of people in a particular category. Okay? It's really important that you know that, because when we ask questions about the proportion, you need to know what those answers look like. And if you're going through a problem and it's talking about averages and you use the word proportion, then your answer is completely wrong. So you need to make sure that you understand what is the difference between an average and a proportion. You need to make sure that you write down the correct words when the problem has to do with proportions, and you don't use the word average because it's not an average. A proportion is a percent of people in a specific category. It would be like, did you go to a concert in La Crosse last year? Or have you seen Neil Diamond in concert? Most people haven't. Things like that, okay? Or how many people reported that they actually felt better after taking this medicine? Or what percent of students actually come through a preschool and are successful in kindergarten? Those are the kinds of things we're asking here. We're asking questions about percent of people in a particular category. That's what a proportion is. Now, this is not the first time I've said this. This is in your notes, but I'm really glad if you write it down right now, because then you'll keep track of it. Because this is really important. You need to know what this is compared to an average. An average is not a proportion. A proportion is not an average. When you ask a question, here's 10 problems on the test. How do I know which kind to do here? You're going to look for these kinds of ideas in order to know how to do the problems on the test. And if you get it wrong, it's completely wrong. So you need to make sure that you know what a proportion is. Now, how's that different from a mean? When we're doing a measurement of the mean, we're not talking about putting people into categories. We're actually measuring a number. Like, what's your blood pressure? How much money did you spend last month on a thing? Okay? And then the mean is, hopefully you understand, the average. Okay? Now, somebody tell me the definition of a standard deviation. What is the standard deviation telling us, if I know what that number is? It is the measure of the variation of a data set from mean. So the standard deviation is telling me how much variation or difference or wild swings of numbers in a number, okay? So the mean and standard deviation are related because we're measuring numbers of a thing, a certain amount of a thing, like blood pressure or whatever else. Proportion, we're measuring how much percent is in a particular category. So you need to know the difference between those kinds of things. Now, we've already done this with confidence intervals. I want to know what are the symbols for the sample and for the population for these different things. What symbol do I use for the sample portion? I use p hat. What do I use for the population proportion? Sample proportion is p hat. What's the population proportion? Just p by itself. What's the sample mean symbol? It's R. What's the population mean symbol? U. What's the sample standard deviation? Sample or population standard deviation? Small sigma. All right, there we go. So what's going to happen when I do a confidence interval is that I measure a sample, and that tells me something about a population, but it's an interval. So if I say something like, how many people are going to vote for this new law or approve of this new law that's going to come out? Well, I would say something like between 35 and 45% are in favor of this new law. So I would have some kind of interval that tells me where the population number is. Same thing is true for mean and standard deviation. I'm going to have an interval that tells me where the population number actually is. Now, this is useful and helpful and good, and some people say it's the best way to do the things. But we also have to understand hypothesis testing. Hypothesis testing, which we talked about last time, is a different way to think about how this works. With hypothesis testing, the basic thing that's happening here is that we are trying to prove a difference. Let's take an example. Let's say that I measure the sodium levels of everybody in this classroom, and I come up with a number. Say it's 175. That will be my X bar. If I come up with this as being the sodium levels in this class, what if I have some number out there and I say that the population mean, or the mean for, let's say, people in the USA is 125 or 120, let's just say. Is it reasonable to say that the average of this class represents something that's higher than this 120 right here? Unfortunately, you can't answer that question because you don't know how much variation there is in this number. If this has a standard deviation that stretches all the way out here, okay, if this is a number that could be very high or very low and you don't know how much variation is in this number, this could be just a random chance that this is 175. So without knowing how much variation there is in these numbers, you can't really say what's a high number and what's a low number. So we have to, in order to understand how this works, we have to have some way of actually coming up with mathematical ways to say this is significantly different. Okay? When we say significantly different, again, we're talking about two possible choices. Either it's going to be significantly different, or it could be a random fluctuation. It could be that this is just chance that created a difference between these two numbers. And so with hypothesis testing, I want to come to the end of the thing and say, I know for sure that this is a significant difference. If I can't say that, then I'm not able to say what's really happening. If I get to the end and I cannot prove that it's significantly different, then I really don't know if my group is higher or if it isn't. It could be a chance, but it might not be. It could be that all these people have huge things with sodium going on, but I don't know the answer to that question if it's possible for it to be just by chance. Okay? So what we're going to deal with then is going through this process, which is on this sheet that I handed out to you. Okay? So we're going to state the hypotheses, identify the claim. Then we need to find the critical value, and I'm sorry, you need to write this in there, and the rejection region. Okay? So you're going to find the critical value. You're also going to find the rejection region. It's part of step 2. Let's see if I can make that happen. Rejection region. There we go. Critical value and rejection region. Okay. The third part then is to compute the test value. Now, when we're doing test value, this is something that you would have in the important formulas and tables. Chapter 8, hypothesis testing. It's giving you these formulas. We'll talk about them. Okay. And then that's step 3. Then step 4 is when we make a decision. We're going to go either one of these 2 directions. And then at the end, we summarize the results. That's these things 1 through 7. These 1 through 7, which are the parts of a conclusion. When we summarize the results, that's what we're going to be doing. Now, these steps 1 through 5, when it says solving hypothesis testing problems, those are actually in your textbook and they're on that sheet of important formulas and tables. Okay? The parts of a conclusion, this is what they do. They don't tell you, so I'm telling you. All of this information will be given to you on the test. Okay? So you don't have to memorize all this, but you do have to know how it works. All right. So does anybody have any question about anything right now before we do this problem? Okay, so we're going to do this problem. Do it in a pop-up? Sure. There we go. Whoa, they're destroying the world next door. Okay. Now, what happens when people look at a problem like this? They immediately look at it and they say, it has too many numbers, I give up. That's probably not a good idea, all right? What you need to do is you need to think about what kind of problem you have and think about what you're looking for, okay? So, the percentage of physicians who are women is a blank thing. You don't need to worry about that number yet, just keep going. In a survey of physicians employed by blah, 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 okay? Who cares? It's just a survey, all right? Somewhere out there. We'll come back to that later. 42 of 115 randomly selected physicians were women. Is there sufficient evidence at 0.05 level of significance to conclude a thing? All right? What you have to be able to do is find those phrases that you can put into different categories. And if we say, I want to determine the hypotheses, okay, what I'm looking at is the question. What are they asking me about? And the first thing I'm going to do is figure out which of these 3 things are we talking about. Are we talking about proportion, mean, or standard deviation? So if I look at this, can you tell me which one of these 3 things am I doing? We're doing proportion, okay? So then, when we're doing proportion, what we're talking about is people in a specific category out of a total number. 42 out of 115. As soon as we see that, then that's telling us to how we're going to find p hat. P hat is going to be the number of people observed divided by the total, which is x over n. It is not the letter P. It is p hat. Okay, so what happens when we do that? What do we get? We get a really long number. We do not want to round this off too much. Okay? While we are in the process of doing a problem, we do not want to round off. At the end, rounding off is not going to matter. But during the problem, we want to make sure that we keep enough digits of accuracy to make this work. Okay. So we're going to call this 0.3652. Okay. Now, as soon as we get p hat, all right, then we know we're going to find something to compare it with. There's got to be, in these situations, there's some kind of a standard number that we're looking at. And what we've got here, now we need to pay attention to what's being asked. What did we observe? The number of women out of the total, 42 out of 115. So we're looking for a percent of women to compare to this number. And that would be what? 27.9. All right. So this is a percent or a proportion. The one that we're going to compare it to is 0.279. So this is a sample proportion, the first one. The second one is the population proportion. And what we're trying to prove is a difference. So when you look at the problem and you say, okay, where is this difference that we're trying to prove? I look at p hat. It's a higher number than letter P. So what I'm going to try to do, which is what the problem asked me, does this proportion exceed 27.9? Is the proportion larger than the 279? Now, of course, it is larger. But the question is this a significant difference? Or is it just something that could happen because of the random nature of things? Is it just by chance? And once again, we don't really care about the sample number. What we want to actually prove has to do with the population. Is our population in this university health system, is our population higher in percentage than the 27.9? We're assuming the 27.9 came from like a national survey. Ours is larger, but this is not everybody. This is just a sample, supposedly. All right. So then, when we're going to set this up, we're going to have the null hypothesis and the alternative hypothesis. The null hypothesis will always have an equals sign. And then the alternative hypothesis depends on what direction we're trying to prove. Okay. So in this case, when we say exceeds, that means more than. So we're going to use the more than symbol.
So the first one is a null hypothesis?
That's correct.
And what's the one with the alternative?
Alternative. Null hypothesis and the alternative hypothesis. So then, what we're talking about here is trying to figure out something about proportion. So that's why we put the letter P here. And what are we comparing to? 0 to 79. Now, what I have just done would be one question on the test. Here's the situation. Tell me the null and alternative hypotheses. That's one question. Okay? And then I move on and give you something else. So you don't have to do all of the problem from top to bottom on the test all the time. You will have one question that looks like that, but most of them will be, here we are going through a problem, what's the next step? And then you do that next step, and that's the question on the test. Okay. So it's really important for you then to understand how to read a problem and come up with the hypotheses, which we just did. We look at the problem, we say, what's being measured? Proportion. So I know it has P. I know the first one has an equal sign. What's the direction of the next one? Well, it says exceeds 27.9%, so that means it's greater than 0.279, and the first one is it's equal to 279. So now we're going to go through the process to try to figure out, is there a significant difference? All right, so when we say the claim, all right, this is a bit confusing, but hopefully we can make this work. What the question is asking me is evidence to see the greater than. Okay. Sometimes, occasionally, it will claim that it's equal to 0.279. But most of the time, what we'll be claiming is the greater than or the less than. Okay? So when you read the problem and you say, what are they trying to tell me? They're trying to tell you it's greater. So that's the claim in the situation. All right, so then, the next thing that I want to do is to figure out the critical value and the rejection region based on the correct table. When we're working with proportions, you might remember that proportions, we use Z. For the mean, we use T. For the standard deviation, we use chi-square. So you need to keep track of this. When we're talking about doing proportions, we're looking at Z. For the mean, we use T. For the standard deviation, we use chi-square. Those are the three things we're going to be using for this process, just like we did for confidences, or in a similar way. Okay. Now, when we look at this for the hypotheses, I'm going to draw a picture, and because I know it's proportions, I'm looking at the Z, which has a 0 in the middle. And then I want it to be greater than, so that's out here. Because it's greater than, then that tells me it's a right-tailed test. If it had been less than, it would be left-tailed. Greater than, it's right-tailed. Okay. So what I need to figure out then is, what is my Z-score for that thing out there? Now, there's one way to make this happen that's a bit easier than in what it might be otherwise. And that is, if we actually use the t-table. If you look at your table, of course, and we go clear down to the bottom of the t-table, you will see that it has the letter Z at the bottom.
Table F.
Table F. If we go down to the bottom of table F, you will see the last line says Z. So that means we could actually use this table to find the Z-scores that we want. Okay? This is where we have to be careful, though. We have to look where it says one tail alpha. We cannot use confidence intervals for hypothesis testing yet. We have to look where it says one tail. When it says 0.05, that's the alpha that we want, and it's one tail. So I'm looking at 0.05, one tail, and I go all the way down to the bottom. What do I see when I get there? 1.645. That's what this number is right now. I'm going to say this another time. You're not going to believe it, and you're going to make mistakes, but I'm just going to keep trying to say this. You don't use the confidence interval to do a hypothesis test. Not yet. So when I say it's 0.05 and it's one tail, you look where it says 0.05, one tail, and you go down to the bottom. You don't look at the confidence interval part. You're looking where it says one tail. It's 1.645. Okay, that is the critical value. And then this part out here, this is the rejection region.
What's the shaded in part?
The shaded in part
Is the rejection region
is the rejection region.
underneath it?
So our Z-score is the critical value?
This z-score, 1.645, is the critical value.
Yeah, but whenever we do this problem, the Z-score is gonna be the same as critical value. Any problem with the ask for the critical value, it's the same as finding the Z-score?
If we're using proportions. Yes. Okay, so we're using proportions. We find the z-score.
Shaded in.
This thing out here is the rejection region. So what does that mean? It means that if I get a z-score greater than this, then it's going to be in the rejection
So
region.
the critical value is where that line is.
Yes.
Point, and the rejection region.
Yes. So what I've just done is part 2. I found the critical value and the rejection region from the appropriate table. Now, if you're really interested in finding this using the z-table, you could. You find where it has an area of 0.05 to the right, and you come up with 1.645. You don't have to do that. Obviously, it's right there in front of you. Well, that's what we're going to do. So then, our next step, according to our list, is to compute the test value. Where does the test value come from? It comes from our formulas. And this is where I don't want to erase anything. So I guess I'll erase this over. So we're working with proportion right now. When we say, what's the formula for the test value? That's on your formula list, and it's z is equal to p hat minus p over this.
Q over N.
Yes, PQ over N. That's an N. Ooh, not a very good one, but. So now is when we need to do the calculation from the formula. But it's important that you know what number goes in here. P hat is the number that comes from the sample. P is the number that comes from the problem statement or from the null hypothesis. So this is going to be 0.3652 minus 0.279 over square root of 0.279 And then we need to know what's 1 minus 279. 721 divided by n. 115 people. Okay, so this is the calculation that we need to do right now. Okay, so
No.
all right, so hopefully you've got 2.061 or something close to that. All right. So in a similar way to doing confidence intervals, right, you have to make sure you keep track of the order of operations. If you're going to use your calculator, you got to put parentheses in the right place. You got to know how that works. If you do these things separately and write down your answers, you might be prone to making errors that way because you have to write down long decimal numbers. It can create a problem. So it's nice if you can get the parentheses to work and you can just make it happen on your calculator and just get that number, 2061. Okay, so let's just say that you have that number. That is your test value. That is step 3. We computed the test value. Any question about that right now? Okay, so then number 4 says make the decision to reject or not reject the null hypothesis. This, of course, since you only have 2 alternatives, you really got to know which one is which. Okay? And this is where sometimes the words get in the way. You should never say, we reject it. Because rejecting it is not the issue. Rejecting the null hypothesis is the question that we have, and rejecting the null hypothesis is the same thing as proving the difference, which is what we want. Okay? So, what does this look like? Once again, when we say that this thing is significantly different, that's going to be reject the null hypothesis. If it could be just a random fluctuation, that is where we say do not reject the null hypothesis. And what's going to happen later on is that you're going to say, we reject it. And I'm going to say, what do you mean? If I reject the null hypothesis, then that means there is a significant difference, which is what we wanted to do, okay? This is our goal. This is what we want. We want to do this. We want to reject the null hypothesis. Why? Because the null hypothesis says that it's equal to 279. I do not want to prove that it's equal to. I want to prove that it's greater than. That's what we want to do, is prove a difference. So when we use the term reject the null hypothesis, that means we are rejecting the status quo. We're rejecting equality. We are proving a difference, which is the only thing we can do. We can only prove things are different. And we want them to be that way in this situation. We're saying, I want to prove that this university hospital is different from all those other hospitals out there. That's what we want. So when we say reject the null hypothesis, that's what we want to do. And that means we have proven that they are significantly different. However, this is where it gets rough. What if that didn't, yeah, that's right. What if that didn't happen? What if we did not reject? Then it could be that this is just a random fluctuation. It could be, well, we just happen to find a larger proportion of women in this thing. And that would be a sense where we do not reject the null hypothesis. And what we say here is no decision.
What is that value? 2.061. I know it's a test value, but what information does that give us?
I'm about 3 seconds away, so there we are. Okay, so now that we know what we're trying to do, we are trying to make the decision to reject or to not reject the null hypothesis. This is where we say if the test value is in the rejection region, then reject the null hypothesis. Unfortunately, there's a lot of conversation right now, and right now I just told you something that's going to make a big difference in your life. So if you're able to pay attention to this right here and to write it down, that would be a good idea. We'll start over after we get done. We're going to finish first, and then we're going to start over. Okay, we're not done yet. So we're going to finish, then we're going to start over. Okay? If the test value is in the rejection, we will reject the null hypothesis. Where is my test value? 2.061. Where is 2.061? It's in the rejection region because 2.061 is out here. This is my test value. Now that I have my test value and it's in the rejection region, I will say reject the null hypothesis. I have now made my decision. Reject the null hypothesis. I have now just done step 4. I rejected the null hypothesis. I'm now going to do step 5. What does that mean? If I reject the null hypothesis, it means that there is a significant difference. That's our goal. I wanted to prove that there was a significant difference. And the answer is yes, there is a significant difference. So that when I go to this problem and I say, is there sufficient evidence to conclude that the proportion of women physicians at the university health system exceeds 27.9%? Yes, there is. There is a significant difference. My university health system has more women physicians in it, not just by random chance, but there's something going on here that's causing this group to have more women physicians. Even though I only looked at 115 of them, that was my sample, I didn't look at everybody. But based on what I have right here, I am able to say with this amount of confidence that my university health system has more women physicians than the national proportion, or wherever this 27.9 came from. Okay. So, whoever it was that actually said to me, can we start over? We're going to start over right now.
So when you say step 5, so when we get to that
Conclusion?
other test, how much is considered a summary?
We're not going to get there yet. I'll tell you in a minute. Okay? Any other question? Okay. Part 1. State the hypotheses and identify the claim with the correct hypothesis. Step 1 is to state the hypotheses and identify the claim. Excuse me? I'm sorry?
Type that in on the computer.
Okay, right here it says select. So I'm going to click on this arrow and I'm going to select one of these symbols. It's the null hypothesis, so I select equals. It's the alternative hypothesis. How do I know what the alternative hypothesis is? I look at the problem. What's the word that tells me what thing I'm going to pick here? Exceeds. So I click on here where it says more than.
What would be the other word?
Was less than, or is smaller than, or...
Not equal.
Now, we're not going to get there yet. But later on, I know, but we're not going to get there yet. Okay? Right now, we're just going to look at whether it's a greater than or a less than symbol right now. Okay? Now, what number do we want to put in here? 0.279, because that's the number that we were told was from some other place. And we're saying, is our number, is our group larger than that? So the null hypothesis has an equal sign. The alternative has that sign. And then usually what will happen is that this thing is the claim. Because it says, does it exceed? Is it bigger than? So that's my claim. So that's my claim right here. Claim. Oops, sorry.
Because our answer was yes, we're claiming that what they're claiming is right.
Okay, so this thing here is the claim, the greater than one. So if that's the claim, the other one's not. Okay. This hypothesis test is what? Is it one-tailed or two-tailed? It's one-tailed because it's just greater than. So it's a one-tailed test. Yes, it is. So now we have part 2. Find the critical value. How did we find the critical value? We need to look at a table. It's a one-tailed, and the level of confidence is the same as alpha, or the level of significance, sorry. The level of significance is alpha, so that's 0.05. So we look down at the bottom row, one tail 0.05, critical value is 1.645. It says around the 2 decimal places, so we'll do that. All right. Now we're going to compute the test value. Now in this situation, it says round the sample proportion to 3 decimal places. So that's a little bit different than what I had. I did it 4 decimal places here. So if I just go with 0.365, it's going to change my test value to 2.056. But it says to 2 decimal places, so that's no different, 2.06. There's ever a problem where you put something in and it's almost correct, just a little bit off. The software that we're looking at is supposed to be able to say, oh, that's pretty close.
Will you try and see what happens?
I will. If you run into this situation and you ask it to solve the problem and yours is just a little bit off, call me on the phone and tell me, and I will try to fix it. Do not spend 2 hours trying to make sure that you're rounding off things to the 3rd decimal place correctly. Right? So then we check it, and it's happy. Now we need to make our decision. What are we going to do? We have 2 options. We reject the null hypothesis, or we do not reject it. If the test value is in the rejection region, we reject the null hypothesis. But it's important for you to understand what that really means. Reject the null hypothesis, that's what we want to do. We want to reject the equal sign and prove the greater than sign. So when we go here, we say, reject the null hypothesis, which is what we want. Now, if you look at your paper where it says parts of a conclusion, this is not something that's going to be right here, but it's going to come up later, so I want to show you what it looks like. The first thing is that we talk about how much confidence I have. This is not the same thing as a confidence interval. I'm looking at alpha being 0.05, and so I say with 95% confidence. This is not the same thing as a confidence interval. Confidence intervals have 2 tails. This only has 1.
Where did you get that from?
I got this from alpha being 0.05. Since alpha is 0.05, I say with 95% confidence. The second question, is there or is there not enough evidence? And that takes us back here to what we have. If I reject the null hypothesis, then there is evidence. If I do not reject the null hypothesis, that means there is not. Or I should say enough. Enough. So there is enough evidence. Now, what are we measuring? Are we measuring the mean, the proportion, or the standard deviation? Proportion. So what we say is there is enough evidence to support the claim that the proportion, and then part 4, what are we actually measuring? Proportion is a measurement of something. This is a measurement of women physicians. So that's what we're dealing with here. And then we say, where did we get our information? We got this from a large university system. What direction are we proving? That it's larger than, or it exceeds. And what are we comparing it to? Well, in this situation, it's just 27.9. We don't know where that 27.9% came from. But if they had said something like the United States with a national proportion. But all we've done right here is we have said there is enough evidence to support the claim proportion of women physicians in the university health system exceeds 27.9. Once again, we're not talking about the sample here. We're actually drawing this conclusion for the population of the university health system. All of the physicians in the university health system, not just the 115. But out of all the physicians in the university health system, the proportion of women is higher than 27.9. According to this, yes, we have evidence to prove that that's the case. All right. That's one problem. All right. Now, the fact of the matter is, the only way you're going to get really good at this is by practice. That's what we're going to do next. We're going to do another one. All right.
After the break?
No, we're going to do one right Those. Oh, cloth here. Better. All right. Okay, we'll keep all of that. So let me see if I can make this work. Okay.
Okay, I have it. No, it doesn't feel like everyone that's related to our either. Yeah, right about an advocacy organization.
All right. So let me make this work. So let's say that we're looking at students with siblings. And we say, all right, let's go older. Students with older siblings. And I'm making up these numbers, okay? So let's say that the national percent is 27%. A random sample of cross, and I didn't write this time, students, was 44 out of 200. So what's my p hat value? To do what? If I take 44 divided by 200, what do I get? 0.22. That's my p hat. Is that significantly lower than 27%? I don't know that answer yet. Okay? I don't know that answer yet because I don't know if this number varies a lot or varies just a little bit. So I need to actually go through and see if this number is significantly different by doing the hypothesis test. So what I'm going to do, though, is I'm going to say, is the proportion of lacrosse students less than the national? Okay, so that's the statement of the problem. Is the proportion of lacrosse students with older siblings less than the national percent? Okay, so I need to, step one, state the hypotheses and identify the claim. So what's my null hypothesis going to be, and how do I know? I'm sorry, what did you say?
P equals 0.27.
Yes, because that's the national percent, right? So P equals 0.27. So then what's my alternative hypothesis? P is less than 0.27. And again, this is something that would be just one test question. Here's the problem. Tell me the null and alternative hypothesis. Then another test question might be, here is the thing. Find the critical value and rejection region for this. Okay? So we want to know what is the critical value and the rejection region. And in order to make this happen, we're going to say use alpha equal to 0.01. Okay, that has to be part of our problem. If I don't say what is alpha, then you say 0.05. Okay, in this problem it says 0.01, so that's what we're going to use. Okay. Now, in order to do this, we have to understand what that looks like if we were to draw a picture. If we draw a picture, how do I know it looks like that? Because we're talking about a proportion, that means we're using z-scores. So this is a picture of a z or a z distribution with 0 to the. When we're doing proportions, it's z-scores. So I can make a z-score picture. Now, how do I know what to shade in? What does it look like? This is a less than, so that means it's left table. So I want to know what number it is out there, and I want to know what the rejection region would be for this. Okay. And again, like it says, find the critical value from the appropriate table. So we could use table E, but instead we're going to use table F. And it says 2.326. We're looking at one tail, 0.01, all the way to the bottom, 2.326. However, this is on the left. So it's a negative 2.326. That's the critical value here. This is my critical value.
This sheet.
So where's my rejection region?
Anything less than 2.326 says the rejection region.
Less than negative 2. All right.
So how would you write that out?
If you draw a picture, that's okay. Or if you write the words less than negative 2.326, that's okay. Okay. So now we have our critical value. Now we're going to do the test value. So we need to figure out what that number is. Using our formula, we need to know which numbers are going to go in which places here. I know that p hat came from the sample, so that's 0.22. So this is 0.22 minus 0.27 over square root of, and it's kind of a good idea to put the right thing in here, 0.27. And then this would be 0.73 over what's in 200. All right, well, I give up. We'll take a break and then we'll come back and finish. All right, so I'll see you at 4:23. And then we'll make the rest of it.